Alright, so carrying on with our look at probability, but now we're going to talk about multi-stage experiments, so where more than one event is happening. So independent events are events whose outcome has no, and that should be effect, so effect on other events. So it doesn't matter. An example of that would be, I guess just tossing a coin. I mean, what happens in the first coin toss has no effect on what happens in the second coin toss. They're totally independent results. So if that's the case, then to work out the probability of them all happening, we just multiply the probabilities together. That's what we were doing in those tree diagrams. We were saying, we've got several events happening, we just multiply the properties, multiply along the branches and we'll get them. So, a game of Yahtzee. Okay, we roll 5 dice in Yahtzee, and well, we're going to work out the probability of rolling exactly 4 6s. Well, there's different ways we could do it. Imagine that's just the order of the dice, 1, 2, 3, 4, 5, 6. So I could get a 6, a 6, a 6, a 6, and then not a 6. Or I could get a 6, a 6, a 6, not a 6, then a 6. Or I could get a 6, a 6, a not a 6, then a 6, then a 6. Or of course I could get a 6, not a 6, then a 6, then a 6, then a 6. Or I could go not a 6, then a 6, then a 6, then a 6, then a 6. Multiplying the probabilities together for each of those. So all the 6s are 1 in 6 chance, the not a 6 is a 5 in 6 chance. Add those all up, and eventually we get 25 on 7,776 as a probability. Okay, of course, there is an easier way than doing like that. Independent events, the probability is not going to change just because the order is changing. So therefore, I could have said, well, probability of 4 6s, I could have just worked out the probability of 6, then a 6, then a 6, then a 6, then not a 6. I multiplied it by 5, because each of those outcomes had the same things. It had 4 6s and not a 6. It was just the order of the not a 6 that was different. That's a lot quicker, because now I can just go, 5 times, and then a 6 times a 6 times a 6 times a 6 times 5 and 6, and we get the answer a lot quicker. However, if they're not independent, so if the outcome of one has an effect on the outcome of another, then we have to consider different cases. Let me show you an example of that. Two letters of the word lotto. And we're going to arrange them randomly. We want to know the probability that the word we come up with is the word 2, so T-O. The choice of the letters is not equally likely because I've got 1 L, but I've got 2 O's and I've got 2 T's. So if I'd done it like the last one, so this is not true. What I'm about to put down is a mistake. So it would not be true to go, that's okay, I'll just work out the number of ways I can get a T is 2 in 5, so I've grabbed 1 letter. Now I want an O. There's 2 letters, but I've only got 4 letters left now to choose from. So 2 in 4, probability of 1/5. That's not true. Can't do it that way. Because, of course, here's all our possibilities. Now we want the probability of getting TO, and we can see it's actually 1 in 8. There's 3 cases there that the way I did it originally didn't take into account. Which 3? Which 3 hasn't it taken into account? What do you reckon?
The ones that are have same 2 letters, so L, O, T, and T.
Exactly right. Exactly right. Because the order is important here. TO, when we're looking at words, TO is different to OT. So the first one didn't take that into account. It simply said, probability of grabbing a T, then probability of grabbing an O. Whereas the second one is saying, no. But actually, depending on the order you grab that T and the O, you get a different word. Quick little bit of theory for today. So we shall now add 12E to our list.